My name is Scott Blackburn, and I manage automotive field applications engineering and business development in the Americas within Vishay Intertechnology. This video will provide an overview of a unique electronic switch and resettable fuse that can be used in any 48-volt load applications up to 200 amps. As dual Boardnet architectures, that is, vehicles with both a 12-volt bus and a 48-volt bus, are becoming more popular, new modules and components will be required to satisfy the system demands. For example, a high-power, bidirectional 48-volt to 12-volt DC to DC converter is needed to transfer energy in either direction between the 12-volt battery and the 48-volt battery, depending on the electrical demands of the vehicle and the state of health of the batteries. The 12-volt bus will continue to support the lower power loads in the vehicle, such as interior and exterior lighting, powertrain control modules, the infotainment system, and any other basic control modules or functions. The 48-volt bus was created for the new higher power loads in order to reduce the currents and keep the cost of wiring and other related components reasonable. These loads would include electric power steering, air conditioning, engine cooling, electric turbos, and any add-on parallel hybrid inverters for start-stop or traction assist. As the current requirements continue to increase for both 12-volt and 48-volt vehicle systems, there is a growing need to replace conventional mechanical relays with new methods for the purposes of life expectancy and safety. The use of mechanical relays for connecting and disconnecting high current 12-volt loads has been the traditional solution in vehicles for many decades. However, with the addition of high current 48-volt loads, the same type of component cannot necessarily be used due to the increased voltage for the following reason. In a 12-volt system, there is an electric arc that is created between the two contacts when the relay first starts to open with voltage and load current present. This arc will extinguish itself in a matter of milliseconds as the distance increases between the contacts until the circuit is completely open. However, in a 48-volt system, due to the increased voltage, the arc is no longer self-extinguishing unless a much larger contact distance is used to open the circuit. It is still possible to use mechanical relays, but they become more expensive with the additional design considerations, and the life expectancy is reduced due to the extra contact wear and tear. Therefore, in order to maintain the life expectancy and safety requirements of the vehicle, an electronic switch and resettable fuse has been designed that can be used in 48-volt high current load applications. It has been designed to switch loads up to 200 amps at 48 volts on a compact, double-sided, standard FR4 printed circuit board with passive cooling. The design also features a pre-charge function and continuous current monitoring for control and protection. This schematic shows a simplified version of the power stage and will be discussed in more detail in the remainder of the presentation. In order to allow high currents to be switched safely and efficiently, without damaging the components due to thermal stress, the power stage has been designed with discrete high current MOSFETs. The design features two sets of switches, labeled TR2 and TR3 in the schematic, connected in a bidirectional arrangement to handle the high current load. Without this type of connection, the current could flow back through the MOSFET body diode to the battery when the load is deactivated. Each switch consists of 10 Vishay SQJQ160E MOSFETs connected in parallel in order to minimize the resistance and power dissipation. With this arrangement, the total losses can be limited to under 10 watts at 200 amp continuous operation. The Vishay PowerPack 8x8L trench MOSFETs used in this design feature a bond wireless clip construction that results in an extremely low junction to case thermal resistance of 0.25 degrees C per watt and offers an approximately 15% improvement in thermal dissipation compared to a wire bond construction. The bond wireless construction also allows for very high pulse drain currents, and the gull-wing lead frame provides improved board level reliability. In this case, 60-volt parts with a drain-to-source resistance of 0.8 milliohms each were selected, since the eFuse is located very close to the 48-volt battery, and no more than 58 volts will be seen worst case. To protect the MOSFETs from any transients induced by the load through a lengthy wire harness, transient voltage suppressors are required, which will be detailed later in the presentation. Although not used in this design, a top-sided or reverse cooling package is available for applications where the heat needs to be removed from the top through a separate heat sink, rather than down through the printed circuit board to the heat sink, using thermal vias in a traditional configuration. In order to prevent greater damage to the load and protect the vehicle wiring in case of a short circuit, the load current is continuously monitored using a shunt resistor labeled R2 in the schematic. In this design, 4 Vishay WSLP 3921s, each with a 300 microohm value, were connected in parallel to minimize the power dissipation. The voltage across the shunt is fed into a difference amplifier, and then into both the microprocessor for current monitoring and also into a comparator circuit for the overcurrent detection. When a predefined overload current is detected, the controller can quickly disconnect the battery from the short-circuited load due to the minimal time delay associated with the hardware comparator circuit. However, during this short amount of time until the load is deactivated, the MOSFETs can handle a considerable amount of overload current due to the high pulse drain current capability of the bond wireless MOSFETs. In addition, under normal operating conditions, the continuous current measurement is used by the vehicle's body control module via some type of serial interface to monitor the state of health, that is the charge level, remaining lifetime, etc., of the battery. In this design, a current shunt technology was selected, as opposed to another method, such as a Hall effect sensor, for several reasons. To take advantage of the high linearity over the entire current range, to minimize the offset error due to high temperatures, and to minimize the measurement latency and bandwidth limitations. It is also the technology of choice when high pulse currents can occur during overcurrent or short circuit conditions, due to the rugged welded construction. The Vishay WSLP 3921 selected for this design offers the lowest possible resistance values of the surface mount power metal strip series, down to 100 microohms. They also offer the highest power rating of up to 9 watts in this package size. If needed, the WSLT 3921 series extends the temperature range up to 275 degrees C for high ambient temperature conditions, such as underhood applications, or for added headroom with the necessary derating curve. Another feature of this design prevents a common issue that occurs when first connecting the battery to the load during vehicle startup. That is, the potential inrush current due to any uncharged capacitor banks in the load. If this resulting high peak current is allowed to occur, downstream components could be damaged and the battery lifetime could be reduced. Therefore, a pre-charge circuit must be used to limit the inrush current to an acceptable level. In this design, a Vishay MOSFET, labeled TR1 in the schematic, a Vishay Schottky diode, labeled D2 in the schematic, and a Vishay D2TO20 resistor, labeled R1 in the schematic, are used to limit the inrush current to a maximum peak of 5 amps at 48 volts. Before energizing the load, TR1 is switched on for a predefined time, for example 10 milliseconds, and the output voltage, labeled X3 in the schematic, is monitored. If the output voltage has not reached 90% of the input voltage after that time, the process is terminated, with the assumption that there's a short circuit in the load or wiring. If the output voltage has reached the appropriate level, then TR1 is switched off and TR2 and TR3 are switched on to energize the load. Also note that the Schottky diode is used to prevent backflow of the current through the MOSFET body diode when it's in the off state. The Vishay D2TO20 resistor used for the pre-charge function in this design is a thick film technology in a D-squared pack surface mount package and is designed for very high pulse load applications. Since the pre-charge current is basically a pulsed event, care must be taken to make sure the peak power rating of the resistor is not exceeded during that time. In this case, a 10 ohm value is used for the 10 millisecond pulse, which is safely within the capabilities of the power curve shown here and in the datasheet. In order to protect all of the downstream components in any electronics module from high voltage or high energy transients that can be induced on either the 48 volt or 12 volt bus, some type of transient voltage suppressor is typically utilized in most designs. This type of device will absorb the energy contained within the unwanted transient pulse and clamp the resulting waveform to a level which is no longer harmful to the remainder of the components in the module. In this design, a Vishay XMC 7K24CA and 5Ka SMC30A transient voltage suppressor are connected in series, labeled D1A and D1B in the schematic, and located on the output to protect the components against transients from the vehicle load. The XMC 7K24CA transient voltage suppressor features a new Vishay X clamp or snapback technology with an extremely low clamping voltage ratio for suppressing transients to lower clamping voltages than conventional TVS devices. It features a 24 volt working voltage in a bidirectional arrangement and has a very high pulse load capability, up to 7,000 watts for a standard 10/1000 microsecond pulse, all in an SMC package. As you can see from the current versus voltage graphs on this slide, the X-clamp suppressor has a much steeper slope compared to a conventional device, which results in a much lower clamping voltage for the same level of peak current. In order to obtain other working voltages for a specific application, this part can be connected in series with another transient voltage suppressor, for example, the Vishay 5Ka SMC family. In this design, the XMC 7K24CA is paired with a 5Ka SMC30A to provide a 54 volt working voltage with a very low clamping voltage capability. In summary, a new electronic switch and resettable fuse design has been presented that can be used in any 48 volt load applications up to 200 amps. This design also featured a pre-charge function to limit any potential inrush current to an acceptable level and continuous current measurement for use by the vehicle's body control module to monitor the state of health of the battery. This concludes today's presentation. Thank you for your time today. I hope it was informative and relevant to your applications. Please keep Vishay in mind for any discrete component solutions as you forge ahead into any new designs.